Have you ever done this before? Let's say you're on your calculator here and you put in the number 2. Hit enter. Oh, wow. Okay, that was interesting. Now let's say I take that number 2 and then I just multiply it by something. I'm going to multiply it by 3 here. And it says answer multiplied by 3, that last answer multiplied by 3, right? And then what you do is just hit enter over and over and over again. So it's just taking that last number and multiplying it by 3 over and over again. And this is generating a sequence of numbers. And that sequence of numbers is getting bigger and bigger and bigger and bigger and bigger. It's being multiplied by 3 every single time. And this type of sequence is called a geometric sequence. And we're going to see how it is that we can write a formula for that in 2 different ways, recursively and explicitly. Here, let's take a look. A sequence of numbers is geometric when the ratio between 2 successive terms is constant. Ratio, of course, means I'm dividing my 2 terms. And this ratio here, we call that thing the common ratio. All right, so let me just write down the terms of the sequence that we were just looking at. So we started off with a number 2, multiplied by 3 and got 6. And then by 3 again got 18. And then by 3 again, 54. Did it one more time. I think it was like 162. And then, you can just keep going. So it'd be nice if we had a way to denote what term of the sequence that we were talking about at any given time. And so this is usually what we do. I'm going to call the first one a sub n, little subscript n. The subscripts like you see in the little slope formula, y sub 2 minus y sub 1. It's that kind of thing. All right, and then the second one, of course, is going to be a sub 2. And then we have ourselves an a sub 3, a sub 4, a sub 5, and so on. And so like what the goal here is to find a formula for the nth term. What's it equal to? So like if I wanted to find just the 13th term, I would have a formula. I can just stick my numbers inside and get what the answer is without having to get all the stuff that came before it, right? That's what we want to do. All right, so let's talk a little bit more about this thing that's called the common ratio. Common ratio, when the sequence is geometric, it just means this. When you take the second term and you divide it by the first term, 6 divided by 2, in this case you get 3. That thing, of course, is the common ratio. It should be the same no matter which successive terms that I divide. If I go and I divide, let's say the third one, 18, by the second one, I also get 3. If I get the fourth one, 54, divided by the third one, 18, I also get 3. So in general, this is the way that we write this. That if I divide the nth term here, a sub n, by the one that came right before it, if the nth term is the generic term, what term came right before it? Well, if this is the third term, you'd have to subtract 1 from 3 to get the second term. If this is the fifth term, you have to subtract 1 in order to get the fourth one. So this is going to be a sub n minus 1. The n minus 1, all of that is inside the little subscript. You don't subtract 1 from this term. You subtract 1 from the little index that's down there at the bottom. All right, so we're going to call that r. And this r here, that's the common ratio again. Now, we're going to use this whole idea here in order to develop a formula for this type of sequence, this geometric sequence, and we do so recursively. Well, what the heck does that mean? Writing a formula for a geometric sequence can be done recursively, and a recursive formula generates a give. How about given term of a sequence using previous terms. In order to find the fifth one, you first have to know the fourth one. In order to get the fourth one, you have to know the third one, and so on. Sure, there's a bit of a drawback for this, but it's going to get us started at least on how we can write ourselves a formula for a geometric sequence. All right, so I'm just going to grab these numbers right here again. And here, I'll just copy and I'll paste it back down here. So I'm going to write it all over again. Fantastic. And I'm just going to rewrite these terms in a slightly different way so we can see how this recursive formula is going to work. So there's really nothing to do here with the 2, but the 6, remember that 6 came from 2 times 3. And that 2, of course, was the previous term. Actually, I'm going to write it like this, if you don't mind. I'm going to write like 3 times 2 here, because this 3, hey, what is that 3? Remember that 3 here, that's our like our common ratio thing. So I'm going to start off with that thing here. Here, I'll even highlight there's common ratio. All right, and then that 2 here, that's just our first term, this a sub 1. And I'll write that like this. So this is 3 times a sub 1. All right, this 18, I can write that 18 as 3 times 6. And again, this 3 is the common ratio. I'll highlight it again, common ratio. And what's the 6? That 6 is the term that came right before it. It's the a sub 2. So this is 3 times a sub 2. Right, keep going. The 54. 54 is 3 times 18. 3 as our common ratio, and then the 18 as the third term in the sequence. So this is 3 times a sub 3. Can you see where this is going? The 162. What was that? That's 3 times 54, which is the previous term. 3, common ratio. 54 is a sub 4. All right, so if we try to generalize this, we're going to get this thing that's called a recursive formula, which is going to be based on the term that came before it. So let me erase this little a sub n here, and I'll just write a little formula in general for what we have here. So this one is equal to 3, which is our common ratio, times, and if I wanted to find the second term, I use the first one. If I want to find the third term, I use the second. Fourth uses the third. Fifth uses the fourth. So the nth is going to use the a sub n minus 1, the term that came right before it. Now, if we look at this thing as our formula, we do need one other piece of information. Like, you have to have a term to start it with. So I'm going to add the little extra bit that says that a sub n was 2, like that's what it started with. Now, let's look at this formula right here. This 3, of course, write it one more time, is our common ratio. And that common ratio, previously I defined that as R. And notice that basically I could get the formula that I just wrote if I just multiply this a sub n minus 1 over here to this right-hand side. So this gives us a general formula for the nth term of a geometric sequence. Whoops, that should be R. A sub n minus 1. There you go. So here is our general form for our recursive formula for a geometric sequence. Now, of course, just like I did over here, I do need the first term to start, or actually just any term to start, right? But usually it's the first one that you're given. Okay, now the drawback for this is, in order to find any term in that sequence, I have to know something that came before it. I can't just find the fifth term, because to find the fifth term, I need the fourth. And to get the fourth, I need the third, and so on, right? So there's kind of a drawback there. So another way to write a formula for this type of sequence, this geometric sequence, is an explicit formula, and that explicit formula is going to be exponential. Let's look at that this time. So let me paste these numbers once again. So again, you can see that geometric sequence can also be written in explicit form as an exponential form function. That simply means that whenever I put in the number 5 into my formula, I get the fifth term. I don't have to know all of the stuff that came right before it. So here, let me paste these numbers again. And let's see another way to write these terms. So the 2, nah, I can't do anything with that. But again, this 6 was 3 times, no, oh, actually this time I wanna flip it around. So 2 times 3, okay. And then the 18 here, I'm just gonna write it all out just like I did before, which was 2 times, let's see, 2 times 3, but then I need another 3, right? Okay, yeah, so times 3. So you can see that this would be 3 times 3 is 9, and 9 times 2 gives me my 18. Okay, here's another way to write that. So 2 times 3 squared, just like this one would be 2 times 3 to the first power. Okay, and now this 54 can be written as 2 times 3 times 3, and then you multiply it by that common ratio, which is 3 again, which is 2 times 3 to the third. So 3 to the third is 27. That's all of these 3's that are right there. And then you multiply that by 2, and you get your 54. Can you see where this one's going? This one's going to be 2 times 3 times 3 times 3 times one more 3. That's going to be 2 times 3 to the fourth there. In each one of these cases, you have the number 2. Right? And then we're multiplying it by that common ratio, and that common ratio is raised to some sort of power. It makes this function an exponential function. If I go back to this first one, I could actually write this with that common factor of 3, but what would its power be? Well, since it's not actually supposed to be there, I'm going to put to the 0 power, because 3 to the 0 power would be 1. Okay, so now let's say I wanted to write myself an explicit formula for the nth term here. Then what I could see is that I've got the 2. 2 is always present as my first term. And then I'm going to multiply that times my common ratio, which is 3. And then I just have to figure out what the exponent is supposed to be. So here, this one is the first term, and my exponent is 0. My second term has an exponent of 1. My third term has an exponent of 2. And it looks like it's just 1 less than the term. If this term is n, then 1 less than that, just like we saw before, is the n minus 1 power. N minus 1. And this certainly looks like an exponential function, as we've learned about those kind of things. And let me just highlight a couple of things about this. And this 2 that's right there, that is the first term. And that first term, we called it a sub 1, and barely looked like a 1. There we go. And then we also have this 3, and that 3 there is the common ratio. So there you have it. We have a geometric sequence being that kind where the ratio between successive terms is exactly the same. We call that thing a common ratio, and we can write the formula for a geometric sequence in 2 different ways here. The first one is recursively, where we're defining it based on the terms that came before. As you can see here, in order to find the nth term, you need the term that came right before. Or you can write it explicitly as an exponential function, because you keep multiplying by powers of that common ratio that's right there. And in order to find any term, you don't need to know the term that came before it. All you just need is the position that it is within that sequence. If I wanted to find the 5th one, I just plug 5 in here, and it's 2 times 3 to the 5 minus 1, or, as you can see here, 2 times 3 to the 4th.